Hey everybody, hopefully you can hear me. This is, whoops, I'm still trying to get used to this Osmo. This is Amir Caspi from the Southwest Research Institute, and I am up at the Loveland Pass in Colorado, in the Colorado Mountains, up at about 12,000 feet, and we are here with the CATEcor experiment to try and observe the solar corona during the annular eclipse that's actually in progress right now. Normally you can't see the corona during an annular eclipse. The annular eclipse, the moon doesn't fully cover the sun, and that's why the people call it a ring of fire eclipse. It's a form of partial eclipse, basically. But we have made a sort of a homemade coronagraph out of 3D printed parts, and we are going to try and see the corona today with that instrument. So I'm going to turn the camera around, hopefully, and show you what all is going on. All right, so here you can see the telescope set up, and I'm going to show you all of our lovely folks here. Hopefully we'll get a chance to talk to them as things go. That gentleman over here in the beanie, that is Dr. Dan Seaton. He is also with Southwest Research Institute in Boulder, Colorado. He is leading this experiment to try and observe the solar corona. Over here, right there, we have Dr. Matt West, also with Southwest Research. He is lending us a helping hand with aligning everything, getting everything set up. Over on the computer, we have Anna Tosolini. She is taking data for us and making sure that we're observing the sun and that all of our data quality is really good. We have over here in the hat, Dr. Sam Van Kooten. He's also lending us a helping hand. Dr. Dan Zietlow over there is our videographer for the CATE project. And we have Carolyn Johnson, who's visiting us as an observer for this experiment. So let me show you what's going to happen here. That telescope that you see right there is part of the Citizen CATE 2024 project, and that telescope will be deployed across the country to observe the total solar eclipse next April. That weird thing on the front of it is the coronagraph. It is made out of 3D printed parts. You can see right, where is my finger? Right there is a 3D printed sort of sleeve that fits onto the telescope and allows us to align the coronagraph using those screws right there. The occulter is right there, and what the occulter does is it actually goes in front of the sun and blocks the sun from the field of view, and that hopefully blocks the brightest thing in the image and allows us to see the solar corona around it. And what the occulter is doing, let me go around here very carefully. The occulter is mounted on these trusses and is casting a shadow, which hopefully you can see, over the hole that is the aperture that leads to the telescope. And so that shadow is the shadow of the sun. And is blocking the sun, allowing us to see everything else. So let me see if I can show you what this eclipse looks like by putting a solar viewer in front of the camera. And let me see if I can acquire the sun. All right, it's not exactly in focus, but what you see there is the sun, and there's a bite taken out of it. It might be a little difficult to see through that. In fact, it is quite difficult to see because it's not focused in the iPhone. Sorry about that. But whoops, my Osmo is going crazy. Pardon me, please. There we go. This is what happens when you're in the field with a scientist who doesn't know how to use a camera. Let me give you a bit of background as to why we're doing this, and hopefully if we get a chance, we might be able to talk to Dan in a little bit. Turn the camera around a bit. So we are up here in the mountains of Colorado. It is like 29 degrees out here. Everybody is freezing. But the reason we're up here in the mountains of Colorado is because solar physics basically in the United States basically began in Colorado at the Climax Observatory, which is about 15 miles west of here, where the first coronagraph in the United States was deployed by Walter Orr Roberts and Donald Menzel. and we are basically trying to reach our roots here for solar physics. Coming back to the mountains of Colorado to do coronagraphy, we're using the annular eclipse because when the moon is covering the sun, the sky is going to get darker. And it's not going to get fully dark like it does during a total solar eclipse, but it will get almost 10 times darker here. And for those of you who are in the path of annularity, for example, we have colleagues down in Albuquerque who are doing the same experiment on Sandia Peak. It's going to get more than 10 times darker when they reach full annularity. When the sky is darker, it's easier to see the solar corona. Let's see, Dan, do you have some time to chat?
Very briefly.
All right, stand by. Here's your microphone.
Yep.
All right, let me turn the camera around. All right, so this is Dan. Dr. Dan Seaton is a staff scientist at Southwest Research Institute. He is, how many eclipses have you seen, Dan?
A lot. I've seen 3 total and many partial, and I've worked on a lot of other ones supporting them with live data from spacecraft.
What was your first eclipse?
1999, Romania. I was starting my 3rd year at Williams College, and I went to Romania with Jay Pasikoff, who maybe has seen more eclipses than any other human ever in history. And we observed a very solar maximum corona, and that was sort of the start of my solar physics career. It was really exciting.
So what are we doing here? We're looking at an annular eclipse. So, why is this interesting for us?
Yeah, so as I think you probably already said, we're not going to, actually it's not even an annular eclipse, it's a partial eclipse. We're not going to have the sun fully covered, but we have the sun quite a lot covered. And with this coronagraph, maybe we will image the solar corona. This is a really interesting chance to learn about how to build coronagraphs and maybe how to do the process better and cheaper. It's a really interesting opportunity to actually see if we can take some data and test our equipment for the total eclipse coming up in April. And yeah, so, and it's a really good chance to get outside and just do something kind of crazy and fun and see if we can recreate history right here in Colorado.
All right, so tell us about this coronagraph design. It is strange. Nobody's ever tried this particular kind of design before.
So the idea is that the occulter out there is blocking the sun.
Yep.
It's just a little bit bigger than the sun from the perspective of the telescope. The occulter's shadow falls down. It falls on these support trusses, so hopefully they don't get illuminated, and then completely blocks that little aperture that we have on the telescope. So we don't see the sun, we just see the stuff around the sun. And yeah, it's a very novel design. It's pretty simple. Overall, the occulter shape is really very, very, very carefully designed. So hopefully it will work because the moon's going to do a lot of work for us. And I'm just going to ask my team here for a time check.
Yeah, it's 10:10.
Okay, we're going to need to take data, so I'm going to give you the mic back, Amir.
All right.
Here you go.
Thank you. All right. Whoa, we just got some wind that picked up. So if this live stream gets interrupted, I may actually have to go do some data. We're here in the field. Anything can happen. So, and wind is always a problem.
Okay, we're going to take data at 10:10.
So
10:10, yep. Okay.
I'm going to see if I can show you what's on the screen here as I get behind Anna here. There's a lot of glare. Now, the reason, yeah, you can see stuff. The reason that you're seeing the image change and get brighter and brighter and then dimmer and dimmer again is because we are taking a sequence of images that all have different exposure times. So each of these images basically gets longer and longer and longer, then resets to go to the shortest one.
We're done.
The reason we're doing that is because the corona, it's not that bright, and in fact, it gets dimmer and dimmer the further away you get from the sun. It drops off in brightness by a factor of 100 to 1,000 in just a couple of solar radii. And so, a regular camera is not really capable of capturing that full range of brightness in one image. So what we do is we take a sequence of exposures and then we stitch them all together. We take the parts of the image that are not saturated in each one of the exposures and we stitch them all together. And this is what's called high dynamic range imagery. This is the kind of thing that your iPhone or your Google Pixel or whatever smartphone you have basically does automatically for you these days. We're doing it in a different way, but it's the same kind of principle for what we're doing. Now, you might think, why are we doing this for the annular eclipse? We're doing this because this is a practice run, essentially. I mean, it's its own science to begin with. Trying a coronagraph in the mountains of Colorado is just a fun and wacky little experiment. But we are practicing also for the Citizen CATE 2024 experiment. And that is an experiment that is going to be with community participants. So we are recruiting people from communities who live all along the path of the total solar eclipse that's going to happen in the United States, April 8 next year, 2024. And we're going to be providing them with telescopes just like the one you see right there, not with the occulter, but the same telescope and mount and camera. And we're going to be providing them with training. We're going to be deploying 35 teams with this equipment along the eclipse path all the way from Texas through Maine, so that the eclipse shadow passes over every one of those teams in sequence. And we're going to be able to capture a 1-hour movie of totality. The really cool thing is that that is a community participation experiment. The people that we're recruiting for our teams, they are not scientists. They're going to be students. They're going to be community college folks, maybe Girl Scouts, Boy Scouts, 4-H, whatever we can do. And they're going to receive this equipment to be able to help us do real science. Now, very quickly, I just want to show you the camera, which I'm going to zoom in right here. It's tiny. I mean, that little cube on the back there, that is 1 by 1 by 1 inch, right? It is really, really small. And the really cool thing about it is every one of those pixels actually has a little polarization filter on it. Now, for those of you who aren't familiar with what polarization is, light is a wave, and that wave waves in a particular direction. And that's called the polarization angle. And you might be familiar with polarization because many of you probably wear polarized sunglasses. And those polarized sunglasses, like the ones I'm wearing right here, these guys right here, those polarized sunglasses, they filter out particular polarizations of light. This is very useful if you're trying to do something like go fishing or driving and you want to cut out reflections, because reflections are polarized. So guess what we're looking at when we see a total solar eclipse? The solar corona, when we look at it in white light, it's actually polarized, and it's polarized because of the mechanism of how you see it. And so that camera that's right there, every one of those pixels has a little polarization filter that's looking at 4 different polarization angles all at once. And we're going to be able to measure the polarization of the solar corona, which will tell us about the physics that's happening there in ways that you can't do without polarization. Now, we are 15 minutes away from the peak of the annular eclipse. So this live stream is going to probably end in a few more minutes, but I wanted to make sure that anybody who's watching the solar eclipse, if you're watching it now, if you're watching it in the future for a total eclipse, make sure that you are safe in how you watch it. You want to use these solar viewers that Matt is going to hold up right now. That is a solar viewer, a handheld one. Of course, they also make glasses out of that same material, that sort of silvery material that blocks out 100,000 times of the sun's light. You have to use those filters to safely observe the sun, especially during an eclipse, because the sun is so bright it can damage your eyes. Now, there are other ways to try and observe the sun. One of them is to use pinhole projection. So Matt is going to demonstrate a pinhole projector. Hold that up and let me see the projector here. So you see there are 3 pinholes in it. You can see the light that's shining through them. Now they're different shapes because this is an educational tool for the Punch Small Explorer, which our colleague Craig DeForest is leading. That is a satellite mission that's going to launch in mid-2025. Now let's try and do a pinhole projection and see what we can see. Right there, you can see the shadow that's being projected through those pinholes, and you can see that it looks, if I can focus on it, it's a little blurry because they're pinhole projections, but you can see that it's looking very crescent-y because the moon is covering up about 70% of the sun right now. So we are projecting the image of the sun onto the ground through these pinholes. And that's one other way that you can safely observe an eclipse outside of totality. Partial eclipses, annular eclipses, you can observe with these pinhole projectors. Now, let's see. Let me try one more time with the solar viewer through the phone. See if we can see the sun. Just to show you. No, it's very hard to see because the iPhone does not want to focus on the sun. So I apologize for that. All right. So we are getting close to the peak of the annular eclipse. So I am going to start to sign off on this live stream. Depending on how things go, we may potentially sign on again at 11:30. We'll see. But we have to prep for the maximum of the eclipse when the sky is going to be its darkest. That is going to be our best chance to observe the solar corona. So that's Dan Seaton right there leading the experiment. Matt West, Anna Tosolini here.
You want to point at this? This is what I'm getting on my phone.
You get it?
This is what it looks like.
That's what it looks like. Whoops! Right now, it's taking a big chunk out of the sun right now. All right, this is Sam, Dan, Zietlow, and Carolyn Johnson over there. I am and have been Amir Caspi, again with the Southwest Research Institute in Boulder, Colorado. This is the CATEcor experiment, part of the Citizen CATE 2024 project. I hope you've enjoyed this live stream. We're going to be potentially signing on again in like an hour and a half or so. Stay tuned for an announcement if that happens. Otherwise, if you're looking for us, you can find us on Twitter at Citizen CATE, CATE 2024, and you can find our project there. You can also find our website at eclipse.boulder.swri.edu. That's Eclipse like an eclipse, Boulder like Boulder, Colorado, SWRI like Southwest Research Institute, and then .edu. You can learn all about the CATE project there. There will be additional social media coming up in the near future. That's about it for now. Thank you all for joining us. I hope this has been educational and fun. Stay tuned for potential further live streams, maybe, possibly. Otherwise, look for us again at the total solar eclipse next year, April 8th, 2024. I highly recommend that if you haven't made plans yet to go see it, you do it. It is an experience like no other. Talk to you soon. Thank you.